Okay, hello everybody, good morning. What we're going to do today is we're going to show an informal proof of why the sum of all the reciprocals of all the prime numbers diverges, okay? Now, just by means of introduction, you may be familiar with what's called the harmonic series. So you do the reciprocal of every positive integer. And it can be shown reasonably easy that in fact diverges, okay? It's very, very slow, but you can add more and more terms and it increases without a limit, okay? It's set to diverge. As opposed to, say, this series here, and I'll put a little 2 here, because what I've done is 1, the reciprocal of the powers of 2, so a half plus 1 over 2 squared plus 1 over 2 cubed. Now, those of you doing year 12, 13 maths will recognise this as a geometric series with the first term of a half and a common ratio of a half also, okay? And it can be shown, because r in this case is less than 1, it will have a sum to infinity, which turns out to be 1. You might recall this formula here, a over 1 minus r, but you can do it logically. A half, if you add the first one term, you get a half. If you add the first 2 terms, you get a half plus a quarter, which is 3/4. If then you add 1/8, well, you've got 6/8 plus 1/8, 7/8, plus a 16th, well, that's 14/16, plus 1/16, 15/16. And you can see that this tends towards 1, okay? So 1 is said to be the limit. It converges to 1. Right. Now, what about this series here, the reciprocals of the primes, okay? 1 over 2 plus 1 over 3 plus 1 over 5 plus 1 over 7 plus 1 over 11, 13, 17, 19, 20, 30, dot, 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 dot. Does it diverge or converge, okay? Now, in fact, it does actually diverge. Now, and how to prove it? Well, what we're going to do is we're going to assume it converges, do a little bit of math, get a contradiction, and then you might have been familiar with this term, reductio ad absurdum. We reduce it to an absurdity, and therefore we can say our original assumption was wrong. Now, by the way, before I go any further, this is not original, it's not a formal proof, it would never qualify as a formal proof. I had to look on YouTube myself to get a lot of this information, but what I've just tried to do is just try to reduce it, simplify it. It is not a formal proof, but it's just a bit of work to show how it works. What's the next one? 39. Yeah. Okay, so here we have the sum of the reciprocals of all the primes. And it does in fact diverge. How do we show that? We assume it converges. Okay, so now how do we do this? If it converges, it might converge to, just for argument's sake, say 37. Okay. Then that means if everything ends up as 37, adds up to 37, then there's a part where the last few will be less than 1, add up to less than 1, okay? Now, we don't know exactly where that cut-off point is, but let's say that the sum is 37. And let's say, again, for argument's sake, that all these ones here are, say, just slightly over 36, slightly over 36. And this one here, these ones here, to infinity are less than 1, okay? And so this will add up to 37, okay? Now, this is just an example, it's not the case, but we're just going to take this as an assumption, work through it. So what we'll do then, all these, so the next one's going to be 1 over 31 plus 1 over 37 plus 1 over 41, okay? All these we're going to assume add up to less than 1, and we're going to call it x. So we're going to say that x is 1/19 plus 1 over 23 plus 1 over 29 plus 1 over 31 plus 2. Okay? Now, this is less than 1. Okay. Now let's consider the geometric series x plus x squared plus x cubed plus x4 plus x5 plus dot, 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 dot. Okay. Now, this is a geometric series. We've got a first term of x. The common ratio is also x. Right? We know x is less than 1, and if r is less than 1, from year 12 coordinate geometry, sequence of series, there has to be a sum to infinity. The sum to infinity will be a over 1 minus r, which is x over 1 minus x. Okay, which is incidental. The point is, though, that this has a limit. This converges. Okay? Okay, right, so we've got defined x as 1 over 19 plus 1 over 23 plus 1 over 29 plus dot dot dot. To infinity, the reciprocals of all the primes greater than 17. And we consider this series here, and we've established that's a geometric series, first term x, common ratio x, and it has to have a sum to infinity because the common ratio x is less than 1, because we've decided that this is less than 1. This is what our assumption is, that this is less than 1. Okay. So this has a sum to infinity. Right? Now, let's say we have, in general, if we have a number 2 times 3 times 5 times 7 times 11 times 13 times 17 plus 1 on the denominator, this number here is clearly not divisible by any of 2 to 17 primes. Okay? It can't be. That number is divisible by 2, 3, 5, 7, 11, 13, 17, but as soon as you add 1, it's not divisible by any of them. Okay? Which leaves the possibility that this number here on the bottom is either prime or not prime. Okay, this part here is either prime or not prime. If it's prime, then this on the bottom is clearly greater than 19, so it's going to fall into this part. Okay, it's going to fall into x. It's going to be this part of the series here. Right. However, it could still be composite. 2, 3, 5, 7, 11, 13, 17 all multiplied together plus 1. It could be composite. But if it is composite, the only factors it can have to be greater than 17, right? Because we've already proved that it can't be divisible by any of those factors up to 17. So, which means that, so here's an example. Let's say we've got 1 over 18259. Now this may be prime. It turns out it's not prime. It turns out it can be factorised to 1 over 19 times 1 over 31 times 1 over 31. Which can be got from this series here, okay, Q. If we do x times x times x, we can get 1/19 times 1/31 in the next bracket times 1/31 in the third bracket, right? Which means that this here has to be in that, okay. Now, all we have to do now is just put a constant, or variable rather, in front here, times 2, times 3, times 5, times 7, times 11, times 13, times 17, plus 1. Okay? Now, j can be any whole number value. Let's say it might be 20. If we go 20 times 2, 3, 5, 7, 11, 13 times 17 and add 1. Again, it cannot be divisible by any of 17, 13, 11, 7, 5, 3, 2. See? It doesn't matter what multiple this is if we add 1 to it. So it could be prime or not prime. If it's not prime, it's composite. But again, the factors that make up the product of this can only come from 19, 23, 29, 31, dot, 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 okay? Which means it has to be in here, somewhere, okay? Right, so I'm just going to clear this. Okay, so look, in general we have this term here, 2, 3, 5, 7, 11, 13, 17, some multiple of all that, plus 1. Every single one of these terms has to be in that series x plus x squared plus x cubed, dot, 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 dot. Now, if we just, instead of putting 1 there, put a j, and you probably agree that this is going to be bigger than this because j goes from 1 to infinity. So as these terms get bigger, this stays at 1. So the denominator gets bigger, so the overall fraction gets smaller. So this has to be greater than that, right? This has to be greater than that. So, in other words, if we can prove that this converges, then, or diverges, then this one must also. Yeah. Okay, so there's that. We can take out the common factor of j. And this is just like, this here is just a constant, it's just a number which you can take out, like factorise it. This is 1 over j from 1 to infinity, and you probably recognise this. It's just the harmonic series which we discussed in the first few minutes, which of course diverges. So we have a divergent series multiplied by a constant. This would be a ridiculously small number, but it doesn't matter how small it is. A constant times a divergent series is still a divergent series. Because this could be 1 over a trillion. It doesn't matter. We've got an infinite number of terms here. It still must get bigger and bigger. Okay? So we've proven that this diverges. This diverges. This is smaller than this. So this must diverge, because this is greater than that. So this diverges. This is just a part of this. All these terms are in here somewhere. So it means this sequence or series must diverge. If it diverges, then x, remember it's a geometric series. It will converge if the common ratio is less than 1. But we've shown it diverges, so x has to be greater than 1. X was 1 over 19 plus 1 over 23 plus 1 over 29 plus da da da. X is greater than 1, therefore the reciprocals of the primes diverges. Okay? Hope that is helpful.